Okay, how'd you do? Well, the successful recruits in the edge habitat, once again we're going to use an if function to calculate that. We're going to ask if the number of returning adults plus the number of potential recruits is less than or equal to the carrying capacity for the edge, and that's stored in cell F9. If it's true, we'll let all of those individuals in. If it's not, though, we're going to let in the carrying capacity minus those spaces that are occupied by returning adults. We click OK, and that leaves us with 1.1 individuals that have been successfully recruited into the edge habitat. The number that's unsuccessful is simply the potential minus the successful. Okay, well, we're almost done with this model. We've got 2 more equations to enter, and then we can generate our equation that will calculate the population in the next time step. So this will be pretty quick. We've got really just a handful of more equations to go. Down column H, we want to record the total, the final number of recruits here. And the idea behind this particular column is we want to calculate the total, and that would include the returning adults, the number that were successful, that successfully tried and succeeded in acquiring a breeding territory in the core, plus any unsuccessful individuals, that is, those individuals that tried to first acquire a territory in the edge but were unsuccessful. So we're going to need another kind of if function because we can't just let them all in. We've got these 2 caps that we have to deal with. Once again, we'll use an if function. This time we'll ask if this number of unsuccessful individuals is less than the total spots that are empty. After we've taken care of the returning adults and those recruits that were successful, how many slots are left over? So is cell N15 less than K, the carrying capacity of the core, minus the returning adults, minus those that were successful? That's just asking, is there enough room for these unsuccessful individuals? If it's true, there's room, then we're going to calculate our total recruits as the number of successful recruits in the core plus the ones that were unsuccessful in acquiring a territory from the edge. So in this way, we've linked these 2 back to each other, and we've said if this is full, you get your first choice, but if it's full, you're going to try to find a spot in the other alternative habitat. Now, what do we do if it's false? If it's false, then we simply need to fill up and accept as many recruits as we can, but we have to account for those returning adults. So if it's false, we're going to return the carrying capacity, the total slots we have available, and we'll account for those that are used by the returning adults, and we'll fill up all the rest of those slots with recruits. Make sense? Let's go ahead and enter that equation here for cell O15 as well. Here we're going to use an if function, and we'll ask if the number of unsuccessful individuals that failed to acquire a core territory, is that less than or equal to the number of slots that are not taken? So that would be cell F9, anchor that, minus the number that are claimed by the returning adults, minus the number that are claimed by the individuals that really wanted to breed in the edge. If that's true, then we will accept those recruits into the edge habitat And so our total number of recruits into the edge habitats is going to be the number of successful recruits into the edge habitat plus the number of unsuccessful recruits from the core habitat. And if it's false, we'll just return as many as we can. That would be k minus the number of returning adults. Take some time and review these. One thing I always worry about is people just clicking and entering equations without having any thought behind these equations. These all should make sense. Put your video on pause and work through them. Make sure they sink in and make sure that I have not made any mistakes in my equations myself. When you're ready, we'll continue. Our next step then is our generating equation, which will take us through to the next time step. So how many breeders should there be in our next time step? This is at the time we do our census. Well, we're going to count the number of adults that survived through the year and will be returning, and we're then going to add in our total recruits. This is for the core habitat, and we'll do likewise for the edge habitat. The number of individuals in the edge habitat in time step t plus 1 is the number of returning adults plus the number of new recruits. And from this point, we can simply drag our equations through and copy them down, and we'll have our full model in place. And at this point, I always like to click on my equations and make sure that my relative references and my absolute references are tagged appropriately. And you'll know that if you are trying to reference one of these cells and it's being pulled down, you'll know that you've made a tagging mistake. So at this point, let's pull these down, and now we have our population dynamics for 100 years. We've set up a graph that depicts these changes in the population dynamics through time. Let's start off by looking at the core habitat. We started off with 15 individuals, and our carrying capacity is 25 individuals. And the core is very attractive to these recruits. Now, why does it grow in the core? Well, one way to look at that is to ask yourself, do the births exceed the deaths? And in this model, it's a little bit hard to see that so clearly because we've got some age structure built into the model. But one thing we can do is ask, is the recruitment level for an adult equal to or sufficient to offset the adult mortality? And we can calculate that recruitment as the birth rate times the survival rate. Now what this really means is that each female in the core, each breeding female in the core is producing 0.25 offspring per year. That's the recruitment rate. That's the number she's bringing in, and that's after you account for how many eggs she lays and also how those individuals will survive and be recruited into the breeding population. And here we see her mortality rate is just 0.2. 1 minus 0.8 is 0.2. So the recruitment level is higher than the mortality level. This population should be growing because we're more than offsetting the adult mortality. Now this population grows until it reaches its carrying capacity, at which time it flattens out. Even though the core is still very attractive and all of these young are being produced, that habitat is full. And so what happens then at that point is those individuals begin to be fed into the edge habitat. Here's the edge habitat. At the beginning of our simulation, we see that this population is declining. Let's calculate that recruitment rate. 0.35 times 0.5. This means that for every single breeding female in the edge habitat, they are recruiting 0.15 individual into that particular habitat. Their adult mortality rate is 0.2. And you can see that 0.15 is not enough to compensate for that 0.2 loss. And that's what's causing this little dip at the beginning here. Now, where do you see this population rise? You see it rise when the core habitat has reached its carrying capacity, and even though it's very attractive, these individuals must spill out, and they then acquire their territories in the edge habitat, and the edge habitat then begins to proceed. You can see this captured in the blue line, which represents the overall population size. So we see here that the population size starts to be low and then climbs and is reaching some sort of an equilibrium point. So that's our basic ecological trap model. Now there are many different variations of a trap model that are in the literature, and they all have this notion of attractiveness. How attractive is a particular habitat to these individuals? And we've made a key assumption here that this decision about where to breed occurs, and this decision is being made by these first-time breeders. They're cueing into environmental cues or biological cues in making their choice, but it's their very first time in breeding, and we're able now to explore how this attractiveness might really affect these population dynamics. We'll definitely be playing with this model in the sandbox, but just to give you a sense of how the model can be looked at and explored, let's go ahead and change this attractiveness level down a little bit, 0.7. That didn't change too much. We still have a high attractiveness for the core habitats, which have the higher birth rates. How about a little bit more? Well, still not so much of a change, but if we keep going down, eventually we begin to see that if our core habitat is not deemed as attractive, this whole population is going to go towards extinction. With 40% of the animals trying to find breeding territories in the core habitat first, 60% trying to find habitat in the edge at first, we're going to see these populations start to decline. And this is the notion of this trap idea that Jed was talking about. In rapidly changing environments, these animals may be cueing into cues that might be misleading, and they may actually prefer to breed in these habitats that are suboptimal. And you can see that when that happens, it can have consequences for the whole population at large. To summarize this model, we've calculated and have some space for these outputs. We're interested in computing the growth rates for this particular population. And the easiest way for us to do that with this model, since it has some structure to it, it's not quite as simple as our source sink model. We're simply going to calculate lambda down column S, and I'll need to shrink my spreadsheet a little bit more and enter the word lambda here. And lambda, if you recall, is going to be nt plus 1 divided by nt. So if the number is greater than 1, we know the population is increasing. And remember, this is for the full population, not just the core or the edge habitat. So this is our entire population. So our entire population starts by climbing and rising a tiny bit, and then it starts to fall. And we see that here. 1.01, little bit lower, little bit lower. Here we're close to 1, and now we have a declining population where we're declining a little bit every single time step. In the case of these outputs, we can also ask, is the core habitat lambda declining or increasing or stable, and also the edge habitat. For the core habitat, we're simply going to reference the very last entries down column B, because that's our census for the core. So we'll head down to column B and we'll do NT plus 1 divided by NT. And same thing for the edge habitat. What's happening there? That's going to be the last entries down column I. NT plus 1 divided by NT. And we can see here that in this case both of these habitats are showing decline. And of course, as you change these, you'll also change these outputs as well. The growth rate then, since lambda is NT plus 1 divided by NT, we know that the growth rate R is equal to lambda minus 1. So we'll enter R as lambda minus 1, and we can carry that through. And the growth rate is simply going to be equal to this R term, but we're going to express that as a percentage. So that is equal to 1%. And I'll blow this back up a little bit more. So there you have a very, very simple trap model. And there are lots of different models out there in the literature. All of them have this notion of how attractive are these different habitats. And we'll certainly have an opportunity to explore this concept more when we are in the sandbox. We'll be able to test these different notions of carrying capacity and attractiveness, and we'll also really be talking about what kinds of things should you be really concerned about as a conservation manager in terms of these different parameters and rates. So now we'll head back over to Jed, and we'll see you in the sandbox then.
Great, thank you very much, Terry. I hope you found that spreadsheet exercise to be really helpful in terms of visualizing how ecological traps work in a landscape. Not only that, how habitat edges and edge effects sort of play into ecological traps, and how you can build a model that simulates really how a population behaves, how it may persist over time in light of an ecological trap in a landscape. So we've covered a fair amount of material in this module, and just to wrap up, I'd like to point out some of the key points. An ecological trap is a habitat, an area in a landscape that has really low quality. So it has low rates of things like reproduction and survival, right? So it's relatively low quality. And in fact, a population of individuals that may occupy a trap would eventually go extinct because we'd have death rates that would exceed birth rates. So within a trap, a population would eventually sort of swirl down the drain of a sink into extinction unless it received an influx of immigrants from elsewhere, from another habitat, let's say. So ecological traps are very much like sinks, and we've covered sinks in previous modules. An ecological trap is just like a sink, except it is a preferred sink. So the individuals are actually preferring this sink. They're not sort of just being pushed in there. They're actively selecting the use of this sink. And that can have some real conservation implications. Certainly we know that populations that have sinks don't always go extinct. But if that sink, if the selection of that sink becomes strong enough, if that sink is large enough, it can result in the extinction of a population. So if we're concerned with the persistence of a population of bobolinks or vireys or another species, certainly understanding the effect that that trap has on the entire population is important to know, and hopefully you've got the tools to model that in a relatively simple way, in a relatively straightforward system. I will say as a caveat that Not every species has traps in their landscape. And not only that, it's very difficult to identify traps. So we sort of assume that they're out there in a lot of cases, but they're not always out there, and they're very difficult to identify. Why would that be? As you can imagine, it takes very fine-scaled, detailed information on parameters about a population that are not easy to get. Reproductive rates, survival rates, some information about the use of different habitats and so forth. So it can be quite challenging to identify them, although we assume that they may be out there and having an influence for some species. Now, earlier we covered the notion of habitat edges, and edges sometimes occur, or they do occur at the margin of habitats, right? And these edges oftentimes have different conditions. There are a variety of edge effects between, let's say, a parcel of forest surrounded by a landscape of grassland. These edge effects might be increased temperature at the edges, greater amounts of humidity, more sunlight, more predation, and so forth. And these edges can sort of penetrate into our habitat of interest. I mention that because oftentimes these edges, which are good for some species, are not always good for others. And there's the thought that edges for a lot of species, like songbirds, for example, can represent ecological traps. So edges can look very much like core habitat that they're used to. There might be great food, there might be lots of niche space. They really seem like high quality habitats, but they're not, because they might experience some form of predation or higher rates of brood parasitism and so forth that could reduce fitness. So we need to be sort of cognizant of edge effects in light of these ecological traps. Now, in the modern world, of course, we have really sort of changed the nature of a lot of landscapes. We have actually carved them up and fragmented them in different ways. And by virtue of fragmenting, let's say, a continuous forest, for example, into smaller parcels, which we do through road networks and suburban and urban housing developments and so forth, but by carving it up, we are essentially creating a lot of edge. So again, from a conservation perspective, it's important to realize that edges can be very different places, and that by virtue of developing a landscape, we do create edges. So with that said, you should have a good solid understanding of what an ecological trap is, how that relates to habitats and habitat edges, and not only that, how you can sort of model a population that has a trap within it if you know some certain information about your species of interest.